Let's look at solving quadratics. We're going to look at solving quadratics by graphing, factoring, the quadratic formula, and completing the square. The graph of a quadratic function is called a parabola. To find solutions to quadratic equations, we're trying to find the x values that make the equation true when y equals 0. So let's first look at solving by graphing. To find our solutions from a graph, we need to look for the x-intercepts. We then take those x-coordinates, and those are the solutions to our quadratic. We have 3 possible solution sets. Our parabola will either intersect the x-axis twice, giving us 2 real solutions. Our quadratic might bounce on the x-axis to give us 1 real solution. Or our parabola will not intersect the x-axis, meaning we have no real solution. So let's look at a few examples. In Desmos, we can just click on those x-intercepts, and then we take our x-coordinates to be our solutions. So here our solutions are -3 and 4. Our next example, we see we have decimals here, but these are decimals we recognize. We know that these are -0.66 repeating and 0.33 repeating, so we can convert those to be fractions. And so those are our solutions here. We don't want to write these decimals that we see because those are just approximations. Here the fractions represent the number fully, and those are the true solutions. For this example, we have a positive parabola that bounces on our x-axis, meaning we have 1 real root. We'll just take that x-coordinate to be our solution. And then our last example for graphing, we see here that our parabola does not touch the x-axis, so we have no real solution. Now let's look at solving quadratics by factoring. To find our solutions from factored form, we use the zero product property. The zero product property states that if a times b equals 0, then either a or b will equal 0. Think about it. For 2 numbers to multiply to equal 0, one of those numbers must equal 0. And this helps us when we have our factored form, because we know that x-intercepts have a y-coordinate of 0, and we've already looked at the x-intercepts to be our solutions. So if we just set y equal to 0, then we can use that zero product property. So let's look at our first example. Here we have our factored form set equal to 0. And so using the zero product property, we're going to set x plus 5 equal to 0 and x minus 6 equal to 0. And then we solve for x. So we use our inverse operations to isolate x for both equations. And we get our solutions to be -5 and a +6. And that makes sense because if we were to substitute in -5 back into our equation for x, we would get 0 times -11, which does equal 0. Same if we substituted 6 back in for x. We would have 11 times 0 equals 0. So these are the solutions to this equation because these are the numbers that make the equation true. All right, looking at our next example, we took our whole factored form, we set it equal to 0. Now here we see we have a number out front. Now we could think about dividing that 4 on both sides, but we know that that's just going to give us our 2 factors here set equal to 0. Because we know 0 divided by anything other than 0 results in 0. All right, now we have the product of our 2 factors, and the product is 0. So we are going to set both factors equal to 0 and solve for x. So we have our solutions, -2 and +3. All right, let's look at our next example. Here we have the product of two factors set equal to 0. So we're going to set both factors individually equal to 0 and solve for x. Notice here, because we had a number in front of the x in our factor, it was a two-step equation rather than the one-step equations we have been looking at. So here our solutions are a -3/2 and a +6. Okay, last example, solving by factoring. We're going to actually practice factoring. So here we just have to find two numbers that add to give us 5 and multiply to give us 6, because we had that a value to be 1. And so to complete this x puzzle, 3 and 2 will work. So it gives us our factors x plus 3 and x plus 2. And then using our zero product property, we're going to set each factor equal to 0 and solve. So our solutions are -3 and -2. All right, now let's go over solving quadratics by the quadratic formula. So this method is essential when we have irrational solutions. So that means we graph our quadratic and we see decimals we don't recognize, or we're trying to factor and we're unable to factor. That means we're going to have some irrational solutions. The great news about this formula, this method always works. We just have to get our equation in standard form and then set it equal to 0. So here's our quadratic formula. X equals -b plus or minus the square root of b squared minus 4ac all over 2a. And then there's a reminder that your standard form is ax squared plus bx plus c. And remember, if the equation is not in standard form, you must convert it. And if the equation is not set equal to 0, you need to move those terms over using your inverse operations to get the standard form equal to 0. Before we look at a few examples, let's talk about something important we can take from our formula. So the expression underneath the square root, b squared minus 4ac, is called the discriminant. And the discriminant is some value that tells us something important about our solutions or the roots of our parabola. And it's all about the sign of our discriminant. If our discriminant is positive, then we have two real roots. Specifically, if it's a perfect square, we have two rational roots, and if it's not a perfect square, we have two irrational roots. If our discriminant is 0, then we have one real root. And if our discriminant is negative, then we have no real roots, which means our roots are imaginary. So let's look at a few examples. Okay, so here we have our quadratic equation, 3x squared minus x minus 5 equals 0. If we were to graph this, we would notice some decimals we don't recognize. We have irrational solutions. So we're going to start by finding our a, b, and c values because we're already in standard form set equal to 0. So our a value is 3, our b value is -1, and our c value is -5. So now we're just going to use our quadratic formula and replace all of the variables in our formula with these assigned values. So we have x equals -b plus or minus the square root of b squared minus 4 times a times c all over 2 times a. Notice I'm putting every substitution in parentheses. That's because I have to put negative numbers in parentheses when I raise them to an even power, but sometimes it helps to just put them all in parentheses. So now we're going to simplify 3 parts. We have one part here, one part here, and one part here. We're going to simplify. All right, so negative 1 gives us a positive 1. And then our discriminant, we might want to put in the calculator. If we don't have a calculator, that's okay. We can just simplify it in parts. So we have 1 minus, and we have 4 times 3 times negative 5. So we could do 4 times 3, which is 12. And then we know 12 times negative 5 gives us a negative 60. And so now we have 1 plus 61, or 60, which gives us 61. So we get our discriminant to be 61 all over 2 times 3, which is 6. So those are our solutions. And here we do have 2 solutions. One of our solutions is 1 plus the square root of 61 all over 6, and the other solution is 1 minus the square root of 61 all over 6. Okay, let's look at our next example. Here we notice it's not set equal to 0. So that means we're going to add 6 to both sides. And if there are any like terms to be combined, we would do that now. And now we have it set equal to 0, so we can use our quadratic formula. A is negative 3, B is negative 5, and C is a positive 6. So then replacing the variables in our formula, we get x equals negative 5 plus or minus the square root, negative 5 squared minus 4 times negative 3 times 6 all over 2 times negative 3. Okay, so now we're going to simplify it in our 3 parts. Negative 5 gives us a positive 5. Now we're going to figure out our discriminant. So we could put that whole discriminant in the calculator, making sure we don't include the square root. It's just the expression b squared minus 4ac. Or we could take it in pieces by hand. We get 25 minus negative 12 times 6. And that gives us negative 72. And in total, we get 97 as our discriminant. 97 is not a perfect square, so we can't simplify that. And then 2 times negative 3 gives us negative 6. So those are our 2 solutions. 5 plus the square root of 97 all over negative 6, and 5 minus the square root of 97 all over negative 6. All right, I encourage you to pause the video and try this one on your own. Remember to set it equal to 0 first. So let's set it equal to 0 first. So we're going to subtract 4x from both sides, giving us 9x squared minus 7x minus 4 equals 0. So we're going to find our a value, b value, and our c value. Again, those values just come from our standard form. So now we're going to use our quadratic formula to find the solutions. We have x equals negative b plus or minus the square root of b squared minus 4 times a times c all over 2 times a. All right. So now we're going to simplify in pieces. So we're first going to do negative negative 7. So it gives us a positive 7. And then now we're going to simplify our discriminant. So negative 7 squared gives us a positive 49. And then 4 times 9 gives us 36. And 36 times negative 4 gives us a negative 144. And so then adding those together, we get 193 as our discriminant. All over 2 times 9, which is 18. All right, last one, practicing the quadratic formula. So here, we're going to add 3x to both sides. I like to line up my like terms, and we're going to subtract 20 from both sides because we're trying to get this set equal to 0, so we have it in its proper form. All right, so now it's in standard form, set equal to 0, so we can find our a, b, and c values. Now let's solve using our quadratic formula. So we have x equals negative b plus or minus the square root of b squared minus 4 times a times c all over 2 times a. So now we're going to simplify our 3 parts. So we have negative 1 plus or minus. And our discriminant is going to be a 1 minus 4 times negative 11. Which gives us a positive 45 as our discriminant. All over 2 times 1, which is 2. Now, one thing we haven't talked about yet, because it hasn't happened till now. Sometimes our discriminant, we can simplify that square root. Okay, so we're going to simplify the square root of 45. Think of that as the square root of 9 times 5, which we can simplify to be 3 root 5. So we're going to write our solutions, simplified. So we're going to have x equals negative 1 plus or minus 3 root 5 all over 2. And then sometimes we'll be able to simplify these numbers further. If both of these numbers are divisible by 2, we could simplify and get rid of that denominator. All right, so that's how to solve by using the quadratic formula. The last way we're going to look at solving is by completing the square. Completing the square is a method that allows us to convert standard form to vertex form. Just a reminder, here is our standard form, and here is our vertex form. where we can take the vertex to be the coordinates HK. So the process of completing the square allows us to create perfect square trinomials. And to do this process, we just take the b value, divide by 2, and then square that result. And once we complete that square, we will have a perfect square trinomial, and then it makes the solving process easier. So let's see what that looks like. All right, so here we have our standard form set equal to 0. And so since we're solving, we're going to go ahead and move our 11 over. So we're going to subtract 11 from both sides. Now we're going to begin completing the square. So we are going to take our b value. We're going to divide the b value by 2 and then square that result. So 6 divided by 2 is 3, and 3 squared gives us 9. So once we get that number, we're going to add that number to both sides. Adding it to the left-hand side is what completes the square, okay? Adding 9 to the left-hand side completes the square, and then we can write that as a perfect square trinomial. But since this is an equation, if we're going to add 9 to the left-hand side, we have to also add it to the right-hand side. And negative 11 plus 9 gives us a negative 2. All right, now we're going to rewrite our perfect square trinomial as a binomial squared. And if you're ever unsure what this number is, it comes from b divided by 2. So here we got 3, so then we have x plus 3. Now once we're done with that process, we just use inverse operations to get x by itself. So here we're going to take the square root of both sides. And the square root of negative 2 gives us plus or minus I root 2. And then we subtract 3 from both sides. And now we have our solutions to our quadratic. We notice that they are complex solutions. We do have imaginary solutions here. All right, so let's look at this example. So since we're solving, we're going to go ahead and add 3 to both sides. And now we're going to complete the square. So we're going to take our b value, divide it by 2, and square that result. So we get negative 5 squared, which gives us 25. So we're going to add 25 to both sides because adding it to the left-hand side completes our square, so we'll have a perfect square trinomial. And on the right-hand side, it has to be added to keep equivalence here, and we get 28 because we're adding the 25 to that 3. All right, now we rewrite our perfect square trinomial as a binomial squared. And so we have x minus 5 here. Now that we're done with that process, we just use inverse operations to isolate x. So we start by taking the square root of both sides, get plus or minus the square root of 28. And then we know that the square root of 28 can be simplified. The square root of 28, square root of 4 times 7, which is 2 root 7. And we also can add 5 to both sides. So those are our irrational solutions here. All right. So the previous two examples completing the square, that was when a equals 1. If a is not equal to 1, we have to factor the a value out of the quadratic and linear term. So what that looks like, we still begin the process the same, where we need to add 12 to both sides. We don't think about our a value until this moment. Because a is 4, we're going to factor 4 out of our left-hand side. The reason why I like to move my 12 over is to avoid making the mistake of factoring the 4 out of the constant term. We only factor 4, or the a value, out of our quadratic and linear terms. So that should be 2. Okay, so now we're going to complete the square. But the thing is, we're completing the square on what's on the inside. So we're looking for a term to go here. So we're going to take -2 as our b value, divide it by 2, and square it. So we get -1 squared, which is 1. But remember, what we do to one side of the equation, we must do to the other. So if we're going to add 1 here, we need to add 1 here. However, we did not just add 1 here. We added a 1 times 4. So that means on our right-hand side, we need to add a 1 times 4. All right, now let's rewrite our perfect square trinomial as a binomial squared. So our right-hand side is just 12 plus 4, which gives us 16. And now we can begin solving for x. So we're going to start by dividing 4 from both sides. Then we take the square root of both sides. And then we add 1 to both sides. We notice here we're left with rational roots, so let's go ahead and simplify. X plus 2 is 3, and x minus 2 is -1. So our solutions here are 3, -1. All right, last example on solving quadratics. If you want to pause the video to try solving this one by completing the square, go ahead and do that now. Okay, so first we're going to subtract 31 from both sides. Now we're going to factor -2 out of our left-hand side. Now we complete the square. So we do -8 divided by 2 squared. Gives us 16. Remember, what we do to one side of the equation, we must do to the other. But here we didn't just add 16, we added 16 times -2. All right, now we have some simplifying to do, and we need to rewrite our perfect square trinomial as our binomial squared. So we have -2 times x minus 4 squared equals, so here this is -31 plus -32. So we're going to have a negative 63. And so now we're going to divide both sides by -2. Which gives us a positive 63/2. And now we're going to take the square root of both sides. And we know that if we take the square root of 63 over 2, we're taking the square root of 63 over the square root of 2, which means we need to multiply both our numerator and our denominator by √2, because we can't leave our square root in the denominator. So then that gives us the square root of 126 over 2. And the square root of 126 can be rewritten as the square root of 9 times 14, giving us 3√14. 3/2 √14. And then we add 4 to both sides. Leaving us with our two irrational solutions. Let me know if you have any questions on solving quadratics.